Hi, everybody. We are from Group 2, and today we're going to present for our project, which is the graph neural network-based multi-agent reinforcement learning. So I'm Yuya, and also our teammates Yasin and Gabriel will go into this presentation. So today's presentation will go through 5 parts, which is first the introduction of the study. Second is the introduction of our target environment. The third is the methodology. The fourth is the result and discussion, and last we will have a conclusion. So as first the introduction of this study. So renewable energy is keep developing in global electricity generation. In 2021, it contributes for 28%, and is expected to contribute more than half on 2030 by the data from International Energy Agency. So there comes out the combined cycle gas plants. So it has a power production efficiency more than 60%, which is better than the traditional coal-fired plant, which is around 35% to 40%. So here we implement the correlated GNN MADDPG, which is an integrated application of multi-agent deterministic policy gradient and also the graph neural network. So next, we're going to introduce our target environment, which is the conjoint env. So in this environment, there are two things we're gonna optimize. The first is to maximize the efficiency in producing electricity and steam, which is the two outcome of this plant with required demand. And the next thing is about minimizing the fuel consumption and adjustment costs for sustainability. So there are two approaches we're gonna optimize. So in this environment, the states, so-called states and also the observation, is some parameters like temperature, pressure, relative humidity, demands, and also prices. So as an action to take, we're going to set the turbine's electricity output, and also other settings differ as gas turbine and also steam turbine. And at last, the reward will be the fuel consumption load adjustment, which is a cost bring by action transition and also the unmet demand. Basically, it's those things that we like to optimize, we say as rewards in this environment. So next, gonna pass to my teammate.
Thanks, Yongyang. I'm Liu Yaxin. Today, I will present the methodology of our research. We will focus on the key components, innovation, and the environment setup of our algorithm. Let's begin with the environment setup and the input-output structure. Observation space. At each time step, agent achieve observations that include normalized time, historical actions, sequence of temperature, pressure, and humidity, electricity and steam demand sequence, electricity price and full price. These inputs help agent understand both current and predict conditions. Action space. Gas turbine includes turbine electricity output, heat recovery steam flow, evaporative cooler switch setting, power augmentation switch setting. Steam turbine includes turbine electricity output, steam flow through the plant's condenser, number of cooling tower base employees. Reward function. The reward is calculated to give the sustainable operation. It's considered for some consumption cost, encouraging efficiency, load adjustment cost, minimize cost of transitioning between actions, unmet demand penalty, reducing penalties for unmet electricity and steam demand. Now let's move the algorithm framework that drives this process. Deep deterministic policy gradient. Forms the foundation structure of our approach. It employs actor and critic frame to generate efficient continuous actions and evaluate their long-term returns. Multi-agent DDPG. Extends the DDPG to multi-agent settings by introducing centralized critical learning. This allows agents to collaborate by considering global states and actions while maintaining decentralized execution. Brief neural network. In multi-agent environments, relationships between agents are complex and dynamic. Gene capture these dependencies through iterative message passing, enabling more effective interaction modeling. Corrected GNN MADDPG. By integrating GNN into MADDPG, we model aging correlation and leverage the information in both policy and value network. Entropy regularization further enhance exploration and prevent agents from converting to suboptimal solutions. Next, let's explore the technical details and the innovation. GNN design use GAT convolution layers to process nodes feature and edge information capture inter-agent relationships through attention mechanism. Benchnorm layers normalize the training process, ensuring stability and faster convergence. Policy network outputs the mean and log standard deviation for each agent's actions. By integrating GN, it dynamically alerts inter-agent interaction to optimize strategy. Values network. The joint critic aggregates data and actions information from all agents using message passing and computes the joint Q value through global pooling policy optimization. Hyperparameter optimization. Automated search using Optuna improve efficiency and performance. Interplay regularization encourage exploration and avoid suboptimal solution. Okay, that's all for my part. Next part will given by Gabriel. Thank you.
Thank you, Yaxing. Now I'll talk about the results and discussion for the project. The histogram highlights GNN MARL's tightly clustered rewards near the mean, reflecting its narrower range. The baseline histogram shows a wider spread, aligning with its larger standard deviation. The model also consistently operates in a more favorable reward zone as compared to the baseline. This box plot shows GNN MARL's reward have a tighter distribution as compared to the baseline's wider range. It has a higher median reward than the baseline, and the outliers reveal that its minimum reward is less extreme than the baselines, highlighting the stability of the GNN MARL. This KDE plot illustrates the reward distributions with GNN MARL showing a sharp peak near its median due to its tighter distribution, where the baseline curve peaks slightly left near its median and flattens over a broader range, reflecting higher variability. Overlapping the curve highlights GNN MARL's reward, concentrating in a less negative region, underscoring its superior and consistent performance. The GNN MARL model also achieves a significantly less negative mean reward as compared to the baseline reward, where the error bars indicate reduced variability in the GNN MARL rewards as compared to the baseline's reward. This bar plot highlights the model's superior and more consistent performance over the baseline. So to conclude the project, we have combined a graph neural network with a multi-agent reinforcement learning to optimize gas power plant operations. The modeled dynamic graph structured environments by blending the GNN's relational strength with MARL's flexibility. We also used GNNs to model agent cooperation and competition, boosting the system performance. We also applied Optuna for an automated hyperparameter tuning, improving convergence and robustness. This offers a replicable solution for addressing multi-agent challenges in diverse fields. We tackled the scalability issue and adaptability issues in multi-agent systems for complex environments. This demonstrated the potential for real-world deployment in combined cycle gas power plant optimization. Areas like scaling to larger systems, testing advanced GNN architectures, and improving agent policy interpretability. It also emphasized validating the framework in real-time environments to assess practicality and resilience. We also established a strong base by combining a cutting-edge GNN with MARL and robust optimization to create scalable and cooperative multi-agent systems. Future works could expand it to a larger system and scale the framework to complex multi-agent environments, integrating renewable energy sources. Advanced techniques could also be explored, like graph transformers and attention mechanisms, for better dependency modeling. Furthermore, focus on making learned policies more actionable for real-world operators and validate performance under practical constraints like computational limits and demand fluctuations. Last, refine and expand GNN-based MARL frameworks for a broader application in energy optimization. That's all for our presentation. Thank you.